Section: Introduction. In this section, we discuss recent advancements in diffusion models, which have shown impressive capabilities in various areas, including decision-making tasks in reinforcement learning, RL. These models are particularly good at capturing diverse behavior patterns and generalizing well to new situations, making them valuable for complex decision-making. However, a major challenge we face is the high computational cost associated with the iterative sampling processes needed to produce quality outputs. To tackle this issue, several techniques have been proposed to speed up diffusion, such as using ordinary or stochastic differential equations with flexible step sizes, sampling step distillation, and improved noise schedules. One promising approach is consistency distillation, where a detailed diffusion model acts as a teacher to train a simpler student model. This student model can then generate outputs more quickly while maintaining similar performance. This has led to interest in applying consistency distillation to decision-making tasks. However, current methods either rely on behavior cloning or use few-step diffusion samplers within actor-critic frameworks. While these methods show potential, they have limitations. Behavior cloning works well only with expert data but struggles with less optimal data. The actor-critic approach complicates training due to the need for multiple networks and sensitive hyperparameters, leading to increased complexity and instability. This brings us to an important question. Can we create a more effective consistency distillation method specifically for offline RL? We propose a new approach that integrates reward optimization into the consistency distillation process. Our method starts with a pre-trained diffusion policy and enhances the standard consistency trajectory distillation by adding a reward objective. This helps the student model learn the diverse behaviors of the teacher while also encouraging it to select actions that maximize rewards. A significant advantage of our method is its simplicity in training. The reward model can be trained separately from the teacher diffusion model and the distillation process, avoiding the complications of training multiple networks simultaneously. Additionally, we do not need to train noise-aware reward models, which are often required in other guided diffusion methods. By directly incorporating reward optimization into the distillation, we achieve better performance, faster single-step generation, and simpler training. We demonstrate the effectiveness and efficiency of our method, called RACTD, on the D4RL Jim Mu Jo Co benchmark and the challenging Maze 2D long horizon planning task. Our results show that RACTD outperforms existing methods, achieving an 8.7% improvement over the current state-of-the-art and reducing sampling time by 142 times. Our contributions include 1. A novel reward-aware consistency distillation method for offline RL that allows for single-step generation with improved performance. 2. A demonstration of decoupled training without the complexities of concurrent multi-network optimization or noise-aware reward model training. And 3. Comprehensive experiments showing our method's significant improvements and speed-up. We plan to release our code once this paper is accepted. In the background, we consider the classic offline reinforcement learning setting, where our goal is to learn a policy that maximizes expected rewards in a Markov decision process, MDP. An MDP consists of states, actions, transition dynamics, a reward function, and a discount factor. In offline RL, we assume that the agent cannot interact with the environment and must learn from a fixed dataset of experiences collected by following a behavior policy. Our objective is to find an optimal policy while relying solely on this dataset for evaluation and improvement. Section Summary. In this section, we discuss our novel reward-aware consistency distillation method for offline reinforcement learning, which enhances sampling efficiency and performance by integrating reward optimization into the distillation process. Our approach simplifies training by decoupling the reward model from the teacher diffusion model, achieving an 8.7% improvement over state-of-the-art methods while significantly reducing sampling time by up to 142 times. Section: Diffusion Models. In this section, we discuss diffusion models, which create data by learning to reverse a gradual process of adding noise to training examples. Starting with a clean data sample, we define increasingly noisy versions of it over time, The process of adding noise is often described using a stochastic differential equation, where a standard Wiener process is involved. As we approach the final time step, the distribution of the noisy data aligns with a known prior distribution, usually Gaussian. During inference, we reverse this noise process by following a corresponding reverse time equation that relies on a score function. We approximate this score function using a denoiser network, allowing us to iteratively remove noise and recover the original data. We also explore an alternative approach called the probability flow ordinary differential equation, PFODE, which maintains the same distribution at each time step and can enable more efficient sampling. Our method, called EDM, enhances both the forward and reverse processes by improving noise parameterization and training objectives. Specifically, we adjust the denoising score matching loss so that the denoiser learns to predict a scaled version of the clean data. We train our EDM model using a specific loss function and solve the associated PFODE during inference with a numerical solver. Next, we address the computational challenges posed by the iterative nature of the diffusion sampling process. To speed things up, we introduce consistency distillation, which trains a student model to mimic the multi-step denoising process of a teacher model in a single step. We develop consistency trajectory models, CTM, that predict across different time intervals in the diffusion process. For any 3 time points, we align 2 paths to predict the data at an earlier time. We also ensure that all predictions are mapped back to the initial time using the student model. In addition to the CTM loss, we incorporate a denoising score matching loss to keep the student model's outputs close to the training data. After this distillation, the student model can perform quick jumps along the PFODE trajectory, allowing for one-step sampling. Finally, we highlight the motivation behind our work. Diffusion models have shown promise in decision-making tasks, especially in capturing complex behavior patterns. Common approaches include training these models through behavior cloning, integrating them into actor-critic frameworks, or using them for guided sampling. However, behavior cloning struggles with suboptimal datasets, while actor-critic methods require careful training of multiple networks. Guided sampling can also be challenging for time-sensitive tasks. Our solution is to leverage the multimodal information from the teacher model and guide the student model to focus on high-reward behaviors by incorporating a reward objective directly into the consistency distillation process. This allows us to avoid complex multi-step reward optimizations and streamline the training process. Section Summary. In this section, we describe diffusion models that generate data by reversing a noise corruption process, utilizing a denoiser network for iterative denoising. We introduce consistency trajectory models, CTM, to streamline this process by training a student model to predict clean samples from noise in a single step, while also incorporating a reward objective to enhance performance on multimodal decision-making tasks. Section: Modeling Action Sequences. In this section, we establish the modeling framework for our reward-aware consistency trajectory distillation. When we apply diffusion models to reinforcement learning, RL, we have several options. We can model actions as a policy, model rollouts as a planner, or model state transitions as a world model. While more complex models can be beneficial for long tasks, they also add complexity and computational demands. Therefore, we choose a balanced approach by modeling a fixed-length sequence of future actions based on a fixed-length sequence of observed states. This ensures that the actions we generate are coherent and minimizes idle actions. We define a sequence of past states at rollout time as a series of states from a specific time back to a set length, and a sequence of future actions as a series of actions for a certain length. Both the teacher and student models learn to predict the future actions based on the past states. We can also adapt this framework for goal-oriented RL by including the current and goal states for conditioning. During execution, we can either take the first predicted action and then replan or follow the entire predicted action sequence. Next, we introduce our method for incorporating reward optimization into the consistency trajectory distillation. We use a pre-trained reward model that predicts future rewards based on the current state and action. When the student model makes a prediction, we extract the action from this prediction and use it with the current state to estimate the future reward. Our training aims to maximize this estimated reward, and we define a loss function that combines different components, balanced by hyperparameters. A significant advantage of our approach is that it allows for fully decoupled training of all components. Unlike traditional actor-critic methods that require simultaneous training of multiple networks, our method simplifies the process. Guided diffusion sampling offers an alternative but requires noise-aware training, which can complicate the process. Our approach, however, operates in a noise-free state action space, allowing the reward model to provide stable signals without needing noise-aware training. This separation simplifies training and enables flexible integration of various reward models. Finally, we address the challenge in offline RL where models learn from datasets with varying quality behaviors. While diffusion models can capture diverse behaviors, they struggle to distinguish between high and low reward actions. Our RACTD method transforms the sampling distribution to focus on high reward modes. We validate this through experiments using a dataset that includes both expert and suboptimal rollouts. Our results show that while the unconditioned teacher and student models capture the distribution of behaviors, our RACTD effectively concentrates on higher reward actions, demonstrating the effectiveness of our reward guidance in selecting optimal behaviors. We also discuss the balance between sample diversity and mode selection in the appendix. Section Summary. In this section, we establish a modeling framework for action sequences in reinforcement learning that balances complexity and coherence by conditioning future actions on past states. We then introduce our reward-aware consistency trajectory distillation (RACTD) method, which optimizes for high reward actions by leveraging a pre-trained reward model, allowing for decoupled training and effective mode selection from diverse behavioral datasets. Section: Experiment. In this section, we conduct experiments to demonstrate three key points. 1. The effectiveness of our RACTD method, particularly when the teacher model is trained on less than ideal data. 2. Our ability to accurately capture complex and varied high-dimensional behavior patterns with just one denoising step. And 3. The speed improvements over the teacher model and existing policy-based diffusion models. For our comparisons, we evaluate RACTD against a wide range of baselines, including standard behavior cloning, consistency policy, model-free reinforcement learning algorithms like CQL and IQL, model-based algorithms such as trajectory transformer, MOPO, Morel, and MBOP, as well as autoregressive models like decision transformer, diffusion-based planners like diffuser, and diffusion-based actor-critic methods like diffusion QL and consistency AC. We first assess our method and the baselines using the D4RL Jim Mu Jo Co benchmark, which features three environments: Hopper, Walker 2D, Half Cheetah, with varying quality data. We follow previous setups by using the best performing checkpoint from training for evaluation. Results for non-diffusion models and diffuser are taken from existing literature, while results for diffusion QL and consistency AC, BC are sourced from their respective studies. We report RACTD results as the average and standard error over 100 planning seeds, using specific parameters for all experiments. Our results indicate that RACTD achieves the best or second best performance across nearly all tasks, significantly surpassing the best baseline in overall average scores. It consistently outperforms the diffusion-based planner diffuser in all environments and exceeds the performance of the consistency-based actor-critic baseline in the Hopper and Walker 2D tasks. Next, we highlight RACTD's effectiveness in complex, high-dimensional long-horizon planning and its adaptability to goal-conditioned tasks. While diffuser has shown promise in open-loop long-horizon planning, it requires many more denoising steps compared to closed-loop planning like Mu Jo Co. We demonstrate that our model can achieve better performance with just one denoising step under the same conditions. We test this capability on the D4RL Maze 2D, a sparse reward long horizon planning task where an agent may need to take hundreds of steps to reach the goal. We use different planning horizons for various maze sizes and perform open-loop planning by generating the entire state sequence, using a reverse dynamics model to infer actions. The reward model gives a score of 1 for reaching the goal and 0 otherwise. Baseline results are sourced from existing studies, and RACTD results are reported as the average and standard error over 100 planning seeds. Our findings show that both Diffuser and RACTD outperform previous model-free RL algorithms and MPPI, which uses actual dynamics. RACTD surpasses the diffusion baseline in nearly all scenarios, demonstrating its ability to effectively capture complex behavior patterns and high-dimensional information. Notably, the planning dimension for this task is much larger than that of mu-jo co-tasks, leading Diffuser to require significantly more denoising steps. In contrast, RACTD achieves a substantial performance boost with just one denoising step. Additionally, a major contribution of our work is the acceleration of diffusion-based models for decision-making tasks. The main computational challenge in diffusion models comes from the multiple function evaluations needed during the iterative denoising process. By reducing the number of denoising steps to 1, our approach achieves a speed-up that is roughly proportional to the original number of denoising steps required. To assess sampling efficiency, we compare RACTD with various samplers, including DDPM, DDIM, and EDM, using the same network architecture as our teacher model. We also report the efficiency of Diffuser, noting that its different model architecture and future state-action pair generation may affect its sampling time. We present the wall clock sampling time and function evaluations for both mu-jo co and Maze 2D, with all experiments conducted on a single NVIDIA Tesla V100 SXM2 to 32 GB. Section Summary. In this section, we conduct experiments to demonstrate the effectiveness of our RACTD model, particularly in scenarios with suboptimal data, its ability to capture complex high-dimensional behaviors with a single denoising step, and the significant speed-up it achieves over existing models. Our results show that RACTD consistently outperforms various baselines across multiple tasks, highlighting its superior performance in long-horizon planning and efficiency in decision-making tasks. Section: Results. In this section, we present our results. In the Hopper medium replay scenario, we achieved a 20-fold reduction in the number of function evaluations, NFEs, and a 43 times speed-up compared to the diffuser model. Our student model also required 80 times fewer NFEs and was 142 times faster than the teacher model. In the Maze 2D environment, RACTD significantly sped up computations compared to diffuser, achieving speedups of approximately 57 times, 92 times, and 114 times for the U-maze, medium, and large mazes, respectively, by reducing NFEs by a factor of 256 for the medium and large mazes. We also found that increasing the number of denoising steps improved model performance, demonstrating the benefits of distilling from a slower, high-performing teacher model, which outperformed direct training of a diffusion model with fewer denoising steps. In our ablation study, we examined 1. The effect of the reward objective during training for both student and teacher models. 2. How different reward loss weights influence model performance and training stability. And 3. The impact of increasing denoising steps with our student model. To explore the benefits of including reward objectives in distillation, we compared 4 model configurations: a baseline with an unconditioned teacher and student, a reward-aware teacher with an unconditioned student, a fully reward-aware teacher-student pair, and our proposed RACTD, which combines an unconditioned teacher with a reward-aware student. Our findings, shown in the tables for Hopper medium replay and Walker medium, indicate that while adding reward objectives improves performance at any stage, the best results come from our RACTD framework. This approach allows the teacher to capture a wide range of behaviors while the student focuses on the most effective strategies. Although enhancing the teacher model with reward objectives also boosts performance, it may overlook less optimal behaviors that could be useful in new testing situations, potentially limiting the model's ability to generalize. The reward loss weight is a key hyperparameter that affects both training stability and performance. We plotted the reward curve over 200 epochs of student training with various reward loss weights on the Mu-Jo-Co-Hopper medium replay. With lower weights, increasing the weight generally leads to better performance and stable training. However, when the weight is too high, such as 1.5, we observed initial improvements followed by fluctuations in evaluation as training continued. This instability arises when the reward loss overshadows other losses, leading to erratic training. Our student model is designed for anytime-to-anytime jumps, allowing it to naturally extend to multi-step denoising without extra training. Following a specific approach, we first denoise from the maximum time to 0, then reintroduce noise at intermediate steps and denoise back to 0, repeating this for each step. This iterative process can enhance the quality of generation. We evaluated the student using 2, 3, and 4 denoising steps, and while multi-step sampling improved performance, we noted that the gains did not increase linearly with the number of denoising steps. Diffusion models have become a strong method for decision-making tasks in reinforcement learning. Their integration into RL frameworks typically follows two main strategies: actor-critic approaches, where diffusion models act as policy or value networks, and policy-based approaches, where they directly generate action sequences. Although these methods have shown impressive results on standard RL benchmarks, their practical use is limited by the slow sampling times of traditional diffusion policies. This poses challenges for real-world applications, such as robotics, where speed is essential. To speed up the sampling process in diffusion models, various strategies have been proposed. One notable approach uses advanced ordinary differential equation (ODE) solvers to reduce the number of required denoising steps. Another strategy involves knowledge distillation techniques, where student models learn to take larger steps along the ODE trajectory. Consistency models, in particular, utilize the probabilistic flow ODE to learn direct mappings from noise to the sample space, enabling one-step sampling by learning anytime-to-anytime jumps along the trajectory, achieving performance that exceeds that of the teacher models. Section Summary. In this section, we demonstrate that our RACTD method significantly reduces the number of function evaluations, NFEs, and accelerates computation speed compared to existing models, achieving up to 256 times fewer NFEs in certain scenarios. We also explore the impact of reward objectives and their weights on model performance, revealing that our approach optimally balances the strengths of both teacher and student models for enhanced generalization in reinforcement learning tasks. Section: Consistency models in decision-making. In this section, we discuss consistency models in decision-making. Consistency models have become a promising approach for learning from expert demonstrations in robotics. In reinforcement learning, we have seen several improvements to actor-critic methods by using consistency models instead of traditional diffusion-based value or policy networks, which leads to faster training and inference. These methods integrate consistency loss directly into the training of value or policy networks, rather than creating a separate student model. While there have been initial efforts to use consistency distillation in policy-based reinforcement learning through techniques like classifier-free guidance and reverse dynamics, these methods require two neural function evaluations and do not perform as well as the best existing methods. In contrast, our approach, RACTD, simplifies the process by using a separate reward model and incorporating the reward objective during student distillation, resulting in better performance with just one neural function evaluation.